Yeah, I think we can start. So
perfect.
Yeah. Good afternoon, anyway, everyone. Thanks for joining. And now Miguel will share the screen and start the presentation. There will be time for questions at the end.
Let me share screen. It should be working.
Yeah, we can see your screen.
Oh. I will get the pointer. Perfect. Then we can start. Yeah, the webinar today, the presentation, the topic is about using open tools for techno-economic assessments, specifically applied on low-emission remote energy system. That has been the kind of the main topic of, or the main topic of remote, with several demo case where they are using renewable production, and also storage in forms of electric batteries and hydrogen. My name is, for those who don't know me, my name is Miguel Muñoz Ortiz, and I'm research scientist at SINTEF. And the topics of today, if I can go to the next slide, yeah, is first of all, yeah, a little bit basics on what is a techno-economic assessment. How do we do it at SINTEF? Because that's important. Because yeah, you can always do techno-economic assessment on an Excel sheet, but we try to apply more advanced methodologies. And then how we'll apply it? We'll apply it to remote energy systems that usually are based on different energy sources, such as PV, wind turbines, also different types of storage, such as batteries and hydrogen, as I mentioned before, and how to kind of optimize this kind of the interplay between all these elements to provide a much more robust system. And then I will present HyOpt, which is a model that we have been developing in SINTEF for several years, and it has been applied to several projects. And since I believe it was last year, it has been made open. And so I will go a little bit through all the most important documents so everybody can have access to it and test it yourself. Because then I will show some results and on a kind of generic remote energy systems, such as the one that are the demo cases in remote. And then I try to make it easy for almost anybody to run the code yourself and change the parameters to see the effects on your system. But we'll get to that. And I was thinking of having some questions and answers in the end. So you can also, of course, ask whatever was not clear, or you have any further questions or comments. That's always really welcome. So we start with the very basics. What is a techno-economic assessment? More in general, it's basically an evaluation of the economic performance of a process or product. So this is really broad. In our case, it will be kind of we evaluate the economic performance of a renewable energy system that kind of substitutes traditional energy generation, for example, diesel aggregators in remote areas. For that, we need to take into consideration both technical parameters, as the name says, techno-economic. So it's technical parameters, and that includes conversion efficiencies, for example, how much electricity we get out of the hydrogen, for example, which are the input and output products. For example, an electrolyzer needing water and electricity to produce hydrogen. What is the energy consumptions of all these elements, etc. And of course, we need also to consider the different costs and cash flows involved. That includes capital expenditures, how much you invest in the different components, what are the operational expenditures, the maintenance, for example, consumption of other products. You need to take into consideration financial conditions and also potential revenues if you are evaluating the profitability of your system. And these techno-economic assessments usually provide, it's not like a kind of perfect solution for reality, but it helps guiding you on making decision support for the economic feasibility of a system, a real system. It could be also applied in research, for example, to deploy a new technology which doesn't have a commercial, it's not at commercial level yet, and compared to traditional technologies. And this kind of assessment can be helpful to tackle uncertainty, to try to evaluate the effect of changing specific parameters, for example, such as electricity prices. If they increase, they double, how will they affect the economic performance of my system. If we look now kind of at the main elements, if we consider the techno-economic assessment as the center, we need to consider both external parameters, such as electricity prices, demands our system needs to fulfill in remote energy system. It could be like the communities or the buildings you are connected to. You could also have market scenarios. You want to look at, okay, what is the optimal dimensioning and operation of my system if in the future the price will increase, or if it will be similar to today, or if it will decrease. And in this, kind of the external parameters kind of define the targets and goals of your system. And then you have more internal parameters and variables linked to your process or technologies. That includes the CapEx, which is the capital expenditures, and it involves investments, the operational expenditures or OpEx, which apply to the costs associated with operation, and also technical requirements, as I mentioned before, such as efficiencies or input and output products. And if you put all these elements together and you assess your system with a techno-economic assessment, you can get an idea of the economic performance. And here you use the different parameters. One could be levelized cost of energy. That's kind of really roughly, I will explain that a bit later, the medium or average price of the electricity provided by your remote system during the period of operation. Or the net present value, that's the sum of all cost revenues discounted to today's in time scale. But again, I will come back to this to explain it a little bit more slowly. If we move to the next slide, I want to show you also very important for how we do the techno-economic assessment is how we define the systems. Usually they are based on different components. They have power electronics, connections, cables, pipelines, but we try to make it simple. And we typically do it simplifying our system into a node and flow system. That means each of the main elements here we consider, if we consider like let's call it as AZ1, it's called here, it could be, for example, an electrolyzer, where you need to invest money to kind of increase your capacity, assuming you start from zero capacity. You have some operational costs, you need some reinvestments. And here in this kind of the node representing the electrolyzer, you model the different, for example, the system dynamics, how is the efficiency, what are the startup times and shutdown times, you have extra consumption in these periods. Everything you kind of use all the equations needed to describe the individual element of your system to one node. And then you have flow of products that could include the electricity, it could include hydrogen, it could include, if it's an industrial process, it could be the input and output materials. And of course, if you are acquiring these products, for example, from different markets, you will have to have operational expenditures, meaning the price you pay for these products. And also when your system produces a product number 3, the product, you can sell it to a market to get revenue. But I know this is really abstract. We will come to more specific cases. We focus a bit more in how we do it, because as I mentioned before, you can do a techno-economic assessment just by writing the main cost and the main technical parameters of your system into one Excel sheet, estimate the cost, and then just see how profitable this is. This can be useful in some cases, but we try to apply modeling and optimization frameworks to this kind of studies. That means we model the system dynamics, the cost, the investment cost, short and long-term perspectives mathematically, using the nodes and flows as I showed before. And all these parameters are usually linked to some sort of cost. Let's say, for example, the install capacity of, if you want to install a new PV panels for your system, the investment cost will depend on the capacity and how many panels you are installing. So all these parameters are linked, and one of them might be parameters, which could be the cost per panel, but the number of panels is a variable, and you don't know in principle which is the optimum size of your PV. So all these costs that depend on the variables that are not known yet are summarized together into what is called the objective function, which in this case is the sum of all the costs discounted to year 0 to be able to be comparable. But again, I will show that more graphically later. And the net present value is the difference between income and expenses discounted at year 0. Of course, you are making some assumption. We're building your case, so you can have some parameters that are not 100% sure. It could be like, for example, the price of the PV. You might have estimations, but you don't know if it's you will get the same price, or you will have to vary it. So you can do a sensitivity analysis to see how these individual parameters, which are uncertain, will affect the total system or the total cost of your system. And as a more advanced, to solve this problem with uncertainty of these unsure parameters, you can do stochastic modeling that has been implemented in some of our models. That means that you include several scenarios, both at operational level. It could be like different type of, let's say, days or weeks. You could have like regular winter weeks, regular summer weeks, some specific peak days where you have extra consumption. And then you can evaluate all of these at the same time, assigning some probability for these typical weeks or rare weeks to happen. And the cost associated with that weeks will be summed to the objective function, as I mentioned before. That's what we want to minimize or optimize. But that's more advanced. I won't be going so deep in this presentation. We'll keep it simple. If we show now kind of how the cash flows for our system look like, and what kind of information we can extract from a techno-economic assessment. We see here kind of in years of our project, and you have different cash flows. First, you have to make an investment, because let's assume you have nothing. And then from year 1 to 10, you have some operational expenditures, for example, maintenance or energy consumption from the grid, if it's electricity. And then maybe at some point you need to have some reinvestments to replace broken parts, or maybe some components have a lifetime lower than the total project horizon, in this case 10 years. And maybe you have some revenues. And I said the techno-economic assessment provides you on a view of how the difference between cost and investment and revenues are. But first you need to discount it to year 0. And for that we use the formula of the net present value, which is each cash flows divided by 1 plus the discount rate, and then elevated to the specific year. But not to go too deep into mathematics, the result is that if we discount all the costs, it will look like this. That means cash flows closer to year 0. Oh, in year 0 they are untouched, but the closer you get to year 0, the less they are affected by the discount rate. But this is actually, these are the values we actually use in the objective function. This cost is what we want to minimize, and this is how we can sum all these values together from different years. Also, techno-economic assessment can provide you with an understanding of what are the cost distribution, what are the, if we look at all the costs, we can see how relevant are the investment costs, here the CapEx, also like the reinvestments, how big of part of the pie they represent, and also the operational costs. In this dummy example, it just show that the operational costs are really low, but that changes from case to case. And once we have our evaluation of the system, we can also calculate other parameters, such as the levelized cost, which is really used. It's as I think I mentioned before, it's like the average cost of your, in this case, for a remote system that consumes electricity, is the average cost of electricity. So it's the total cost of your system divided by the discounted production of your system. You discount both ways, so you can compare the two values together. But this case we saw before, it's quite simple. It's a basic example, a lot of dummy parameters. And in the last slide, we focused mostly on the economic parameters. But in reality, problems are much more complex. There are many parameters to consider. And that comes to the point that data requirements and consistency is very important, because if you have a remote system with different components, such as PV or batteries or hydrogen storage, you need to use consistent data. That means, for example, that investment cost of each element should to contain the same amount of information, let's say, so that they should be addable. Or you're comparing two technologies, of course, you have to take into account that the cost cover the same part of the system. Of course, you also need to define the right type of analysis for each case. In remote systems, in the example I'm going to show you, for example, you have a system functioning with diesel generator, and you want to compare with a fully renewable system and some steps in between. So you want to compare the total cost. So you want to have you want to minimize the total cost because you're not assuming any kind of revenue. And as mentioned before, we use optimization in our techno-economic assessment. That's the difference to a kind of traditional or techno-economic assessment made in Excel. And the optimization allows you to provide, once you define your system that has some variables that are decision variables, they are uncertain and they are defined by the model, and they are linked to the cost. So the type of decisions the model makes are for example, in the optimal investments, and that includes the sizing. If you have a combination of PV, wind, batteries, and hydrogen storage, you don't know in principle how big each of the elements has to be. You don't know how many panels you will need. You don't need how big your battery is. But if you model the system in a form of optimization model, you can define those parameters as decision variables, and the model can provide you the optimal combination for the given system. And not only you get the optimal investment decisions, but also the operation. And of course, you can model the system really, really close to reality or really exact, because it's then you get the model gets insolvable. So really often we use linear formulation of physical systems. So we always need to make some trade-offs and compromise to make the problem solvable, but at the same time realistic enough, such as the operation is representative. And yeah, and again, comment related to that topic, if we consider a project lifetime of a renewable remote energy system, we are looking at many years of project, let's say maybe 20 years as the sample I'm going to show you later, but you cannot either model the operation for 20 years with really fine resolution, such as 1 hour. So we have this double system of time structures. We have strategic periods. That means periods or points in time where you are allowed to invest into a new, increase your battery capacity, install a new PV panel. And then you have also operational. You could mute yourself, I think. Yeah, perfect. But you have the strategic periods where you make investment decisions, and then you have operational periods, which usually are more simplified or a shorter period of time than the reality, but this should be enough to be representative. In the case I'm going to present later, we have 20 years of project. You have only one strategic period. That means you can invest in the energy system once at the beginning, and this system should be able to cover the operation for the 20 years. But we're not modeling 20 years. We're modeling only 1 year of operation. That should be representative. And then we have an expected low profile with 1 hour resolution. And the same applies to PV production and wind production. And what we do is like the total operational cost of this year will be multiplied by 20 to get kind of an estimation of the total operational cost of the system. And then I will show you a little bit more in like physically or graphically what kind of information our models usually try to capture. If we have start with a simple system consisting of a power demand, that's it could be like a house. So you have a profile of the different electricity demand with the different appliances during 1 day, just to give you an example of the operation. This is kind of how an operational profile could look like in the model. Here it's only 1 year, but in the case I'm going to show it's this 1 day, and the case I'm going to show is 1 year. And kind of the main driver for this example is that we need to fulfill this demand. So the whole system will be defined to fulfill the 100% of the demand. And then if we consider the traditional system, let's say, of a house, we have electricity from the power grid, where the price of the spot price of the electricity varies every hour. That's this component, but you have other components. You can have electricity tariffs that at the same time could have a fixed component. You just pay a fixed amount of money just to be connected to the grid. It could have an energy component. So the more electricity you buy, the more you pay. And you can also have a power component. That means when you pay based on your maximum consumption at a specific hour. And eventually you could add in your analysis the carbon intensity of the grid electricity. That means since the electricity grid every hour it's combined by different power plants, some are more polluting than others. You can estimate how much your system or your house, how much CO2 emissions it has, or your remote system if you're operating on, for example, also on diesel generator. So those are things that are included in the model and need to be considered to get a good estimation. But then imagine you have this system, fixed system, and you're thinking, okay, is it a good idea to install a PV panel and a battery pack to kind of reduce my emissions, reduce my costs, and make myself a little bit more self-sufficient? And then you think, okay, I need to install PV panels and a battery pack, but you don't know how big or how many of these. So that's what you use the models for. And in addition, you have extra profiles for example, solar PV generation. It's yeah, so that's something we also include in the model I'm going to show you. So your new system will have both fixed capital expenditures, and just by installing new equipment, maybe you have to pay a fixed amount, but you also will have variable capital expenditures. Depending on the size of each component, you will have to pay more or less. You might have to do some reinvestments, as I said before, after some years. And then you have also, of course, fixed and variable operational expenditure. Maybe they are fixed, you have a fixed maintenance every X years. Or maybe you have also some cost that maybe you use any product like, I don't know, I cannot come up with an example, but if you need to have some extra cost depending on how much you produce, that can also be counted here. And of course, we have the PV profile, like how much electricity your solar panels produce. But of course, if you have more panels, you have more production. So the models like kind of gathers all this information together and makes all the decisions at the same time. As I mentioned before, the model also provides with operational decisions. So if in the case of the battery, it will tell when you operate it, when you charge it, when you discharge it. So it will be part also of the optimization in the part of the operational periods. And as said, operation cannot be the whole horizon of the investment because it's yeah, you don't have enough data and it's can be really complex. The model can be too big. So the operation should be representative despite the simplified modeling. And a way to kind of also reflect the operation in the costs could be taking into account degradation, for example, the batteries, depending how you do the cycles. You have to pay more because your lifetime is short and then you need to reinvest earlier. Or it could be also efficiency curves, like depending on how much percentage of the total capacity of your system you produce more or less, or your efficiency is higher or lower. That means it's cheaper to produce at a given percentage of the total capacity. That could be like a fuel cell that usually prefers to operate lower, or it's more efficient operating at lower percentages and not 100%. So this can be, sometimes it's easier to implement in the model, sometimes you need to find tricks, sometimes it needs to be rather simplified. If we go to, for example, other aspects that are important is how parameters or profiles vary. And we try to make our optimization models handling uncertainty. That can be done through different ways. One way is doing stochastic programming, as I explained before, but that's maybe a little bit too complex to go into details now. But you can have different operational and strategic scenarios that are considered at the same time, whereas each scenario has a probability. But in many cases, given the data provided or the data available, it's maybe faster and easier to do a sensitivity analysis. That means you have a reference case where you make your assumptions and then you do variability. You can copies of the system or similar system where you vary one parameter and you see the effect of this one parameter changes into the whole system. And I will show you an example later. So that was a little bit introduction to what are the techno-economic assessment and what are the main elements that we try to incorporate into ours when we use our models. The second part now is this the model called HyOpt, which is an optimization model that we have implemented. This open version is in Mosel. It's a programming language, and I was thinking going a little bit step by step, showing you where all the things are. The open version is in GitLab. It's implemented in Mosel, and it has some scripts in Python to create, for example, to create cases or to visualize results. And it's important to read the information, about all for example, the sources we use in the case I'm going to show, and also follow the instructions on how to get everything installed, because it's not trivial. We're not that making it everything so easily to use to the general public because we don't have resources. But we try to make it open and accessible enough to those who want to try to use it. So I can show you how the GitLab repository looks like. This is the general open HyOpt repository. And you have the first link is the model. And here you have all the information you need. First, a list of all the files, and also like in the README, really important to read how to use it, and how to install Mosel, which is the programming language of this model implementation, and how to use solver, which is once you define the optimization model, you need a solver that kind of finds the optimal combination of decision variables to provide the lowest net present value. So you have all the information here. It's really important to learn. Sometimes it's a little bit too specific, but you want to run the case for remote, you'll have to go a little bit through it. If you go to inside model, you have the scripts. This is it's really useful to read as well, because it will help you to create how to create new cases from scratch. Although I will provide you the remote case that you can use that as a basis and then change different things. You don't want to go too much into detail. And as you can see, it's a lot of things to be done because we are not finished. But at least we have a model you can all have access to, read about it, and test. Then inside of the open version of HyOpt, we have a specific repository for this. I call it the remote case, which is a kind of generic energy system case, similar to the remote demo cases, and I will go a little bit through all the elements of it and how it works. And here you can, again, you should read all the information you want to run it, but I will go a little bit through it later. But you have all the information here. As you can see, this defines a case you can use with HyOpt, and you can see here the link to the model. So when you download all the kind of the case, you also download the model so you can run everything. But if we come back to the open HyOpt description, we also have like a model description where you can see it's a little bit old, but I think it's still really relevant to most of the capabilities of the model. And this is a mathematical formulation, so I can show you. You can just follow the link, and it's here. And I can show you really briefly how it looks like. So it will define, how the time is structured. How do you define nodes? What are nodes, products, and flow? What are the different decision variables, the different equations that describe the system? So you are more into the mathematical modeling. You can go through it and read a little bit more detail how it works. So it's basically kind of the basic information about the open version of HyOpt that you need to know. And if we focus a little bit more in the system I'm going to show you with that we have I created in HyOpt, in the open version of HyOpt, that you can use and test to change parameters and play with it a little bit. I can show you how it looks like. We have a system load that is nowadays provided by a diesel generator that takes diesel from a diesel source. But we want to see the how can we optimally use renewable energies to substitute the diesel generator. So we have solar panels and wind turbines as an options for renewable energy source, and we have electric battery and hydrogen as options for storage. We have for the hydrogen storage consists of electrolyzer that transform electricity and water, but it here is simplified, so it's not represented. Hydrogen storage and a fuel cell that transform the hydrogen back to electricity. If we look into, as I think I mentioned before, we have a 20 years horizon, so we will have one strategic period in this model case where you make the decision how many wind turbines, solar panels, how big will be your battery and hydrogen storage. And then we will have 1 year of representative operation. So we have 1 year load profile, 1 year wind profile, and 1 year solar profile. And this will scale up based on how much we install how many panels and how many wind turbines. So as I mentioned, I will provide this kind of simple case where you can change different things, such as the input data, the profiles, and the case setup. So how many nodes, the connection between nodes, how many cases you want to run, or how many sensitivities, remote to optimize this, such as remote energy systems. You have, when you download the case, here you have this file in JSON. This is here where you define your case, and I will show you how it looks like. It's a little bit, here. So it's a JSON file, so it's a text file, and it follows one of the generic schema of to define the case, and this is in the folders of the open version of HyOpt. So you want to know the details how it works, then you can go there. But if you want to test the model, you can just follow how the structure looks like, and then you add or remove things. So you can see here, for example, the strategic period duration is 20 years, as I mentioned before. We are assuming no CO tax, so you don't pay per emission, but we will restrict the emissions in a different way, as I will show you later. Here you define, for example, the products we are considering. We only need power, hydrogen, diesel, CO2, heat, and water are they are included, I think, but they are not so relevant in the case. We have data sources. That's if you want to add your own profiles. You can give them a name, so you can just copy this part and add it as an extra. You define where your file is located as a CSV, and then you define which kind of time column, because then from the profile you are selecting the specific year you want to use in, or the specific month you want to use into the model. And you select here that the operational scenarios have 1 hour resolution, and here you define the nodes. So it's I don't want to go too much in detail, but you can go into the files and look how it looks like. And here for the wind turbines, for example, you need to define the profile you're assuming, and here you connect it to the wind data profile that you defined before, but I think I will show you graphically in the presentation, so it's a little bit more clear. Because here I show just how you define the wind farm or the wind turbines node. We make it extendable, so it starts from existing capacity 0, so it has no capacity. So you can, in the strategic period, you can decide how much capacity you want to install. You have a capex, which is variable, so it's 1.28. That's million euros per megawatt. And you have some OPEX relative, which I think is similar. It's millions of euro per megawatt per year. Yeah, and as I mentioned already, it's very important to read the README files, both in the case repository, but also in the model, to know the details on how things work. So this is the best way to know how to run the model yourself and to test whatever you want to test, if it changes variable, changing profiles. And as I recommended before, the best or easiest is to follow existing cases the one that I provide for the remote case to make your own case. Although eventually we will try to improve this interface for normal users, let's say, users. And as I mentioned, you have when you define your profiles, that's probably the most tricky part to know how to do it. You have the data sources, as I showed before, and you give it a name and you say where the file is. And then in the specific node, you can provide the same name as data source. So these are connected. So this is the profile file. So this should be in the same folder, or you can give it the specific address in your computer. And remember that the column with time has to be in a date system, because later you will select the specific operational period that you want to evaluate. And all the profiles you use, in this case, for example, we have one profile for the load, one profile for the PV, and one profile for the wind production. All these three has to have the same length and the same cover the same period. In this case, 1 year with 1 hour resolution. And based on this generic system, I wanted to show, it's not a real case, but I wanted to show what kind of data or what kind of information the model gives on what does the optimization consist of. So we have, if we see look at the possibilities of decarbonizing this generic energy system with PV, wind, electric batteries, and hydrogen storage, we can compare it to the select a base case or a reference, which will be the case where all the electricity is provided by the diesel generator. And then we define 6 sensitivities that we compared with the base case based on how much, first, what kind of storage we allow. In the first 3 cases, we just allow batteries. So we have wind turbines, solar panels, and batteries as a possibility to invest. Whereas in the last 3, we have hydrogen storage. And then we test how will our system, the optimal system, look like if we are aiming at 75% emission reduction, 90%, and 100%, to see the effect on the total cost, the cost of each component, the sizing, and everything. And then when we have all these cases, we will compare with each other. We'll compare them with each other, and we can use for that some parameters. I think we will focus on the levelized cost of electricity. So that means how much does it cost every kilowatt hour provided with our system, which is composed by all these elements. And then also the carbon intensity of the electricity. So how much CO2 emission, CO2 kilograms equivalent you have per kilowatt hour provided to your load. So how I did to run it, I created this, you can rate it in here in the remote case file inside the Open HyOpt. Then I go step by step. How do you obtain the required data? How do you run the requirements? And then you should read. But for many of the steps, instead of you having to do the all the coding in the command line, I created this kind of click, this file where you can just click. So it will run the specific parts. And if they work like this, first of all, you need Python 3 that you can download for the website, but probably many of you have it already. And then when we have Python, we can click on the file run 00s. They are 00 to 04 from getting all the requirements to plotting the results. So first you need to kind of install all the Python packages requirements, all the Python packages that are required to run the model, or the scripts that create the cases and run the cases and everything. Then we can generate data profiles, but then you can also use your own. So that's depending on the case. For this case, you need to get the profiles for the load and PV and wind. And this is all, this is all explained. Where do they come from? I think. Because here you have the data sources. So here it explains where they come from. They are mostly open data, but we wanted to make a general case that doesn't have just some open data that can be referred and found to. we also have here all the input data, where like how much it is and the justification and the sources. So you can see where they come from. But of course, all these parameters you can change in the model. So once you have your your profiles, unless you use your own, you can create the case that will kind of take the JSON file here and then create a database, which I will show you here. This one. And the database basically contains all the input data for all the cases that the model will read and solve, and then it will give you the results as well in the database, which are all the tables that have the rest from results. So once you create your case, I will read the JSON, create the case into the database, and then you click on run the cases that it will find for each of the cases. From the 7 I presented before, it will choose the optimal investments or operation of the system for the given the conditions we set. For example, the like the available nodes, like the PV, if it has PV only batteries or batteries and hydrogen, and also including the emission reduction goals. If you want to reduce 75% of the emissions compared to the base case, or if you want to reduce 90% or 100%. And once we run the cases, the results will be stored into the database, and then we can look at the results. We have this plotting script I will show you in a moment, but it's still in beta, so it's not really complete. But I think it's probably much more helpful than just going to the result tables and then looking for specific data. But I will show you in a bit. So this is kind of the 4 processes, or the 5 processes, 5 steps you need to go through to get your results. And as said, I wanted to show you some results so you can see what kind of information you get from the model. If we, and it will be just clicking on the plot results tab, and it will open a window into your browser. And here you can compare. You have here the 7 the 7 cases. And then you will have different tables that will tell you information of different parameters. We can start with the first one. This evaluates the total costs per node, so per element of your system. If you go to the case number 1, you will only have your diesel source, how much diesel you pay, and here you can say the total cost of the node is 0.1399 million euros for the total 20 years. And then we have some costs associated with the diesel operation, like maintenance and replacements, and that's OPEX, like operational expenditures. But this is really simple because you have only one type of cost per node, but you can go to any other case when you have maybe this case where you have everything. And here you can see for each node you have the battery. Here you have wind, PV, battery, and hydrogen, plus the diesel generator, because we are not reducing 100%. So the diesel generators is used to some degree. So here you can look for every node what kind of cost it is. There's a capex, which is the value of the specific cost, which is the value of the total cost of the node. So here you have a really good overview about how much or where do the costs come from depending on the node. You can also look at the capacity installed. Here we see that the capacity is 129 kilowatt wind turbines. For this case, we see, for example, that it doesn't install any PV. It might be that in our assumptions it's too expensive, or the production is not that much. So this is the results are basically based on our assumptions. So this is provides you an overview of the case of the total costs. Here we have a flow diagrams. Here you can compare basically any flow, like any flow of any case, and you have the kind of the pink flow and the blue flow, so you can compare 2 different flows. Let me make an example. We can compare, for example, the battery when we want to reduce 100%. No, let me see. We can compare. We can compare how much energy from the battery goes to the load. in the case when we want to reduce 100% the cost, 100% of the emissions, and only using batteries as a storage, compared to how much do we use the battery. If we have how much do we want to use the battery, we also have hydrogen storage. So we can see, we have to go a little bit closer. Here you can navigate through the 8,760 hours of the year, how the model, how the operation looks like. And then you can see that if you only have a battery, you will use it. It will provide much more electricity to the load than if you have also hydrogen. But that's yeah, it's just to show that you can compare the different flows for any of the cases to see like the differences. But we can also compare how the if we go to the last case when we have both batteries and hydrogen, we can compare. Here we can see storages, how the storage is used. Here we can see the markets. In our case, we have the load, for example. So you can have a look at the load. But the interesting thing here is we can see how the batteries are operating compared to the hydrogen storage. So we see the batteries. In this case, we have, as I remember, both batteries and hydrogen storage. So we see that the battery is used almost constantly every day. Really, we can even go to more detail if we want to look at the specific hour. And then it's used almost every day. So every hour it changes the storage. But if we compare it to the hydrogen storage, which usually has it's better for longer term storage, we will see that the time of charge and discharge is looking much more long ahead. So it's a little bit more seasonal. So you can see here that it's charged this maximum to cover a big part here, probably maybe because there's less wind in this period. So it's a good way to compare the different storage, how they optimally operate. Here we can see this is really similar to the first total cost, but it will tell you the different cost per strategic period. But of course, this is as we have only one strategic period, so we invest only once at the beginning. We cannot compare the different investments because we only invest in once for the whole system. So that's for these specific cases less useful. And we can also compare, remove or add the different components if we want. And this is one of the most interesting and important parts. It's how do we compare all the cases? For example, if we compare here what is the cost of the levelized cost of electricity for our system? How much does it cost to the electricity? Here, I think it's we need to change to euros. This is Norwegian kroner, but it's I think it's just divided by generated power price. Okay, this is per euro. We can see the base case is basically 50 cents per kilowatt hour. But interestingly enough, if we want to reduce 75% of CO2 reduction, we can actually get more profitable systems. So because in the base case, we forced that it will be only diesel. But if we allow the installation of renewables for a 75% of the CO2 reduction, we can actually get a cheaper system in this case with our assumptions. And as we increase the emission reduction, we need to, the electricity cost increase because it has to be a robust system, not relying on diesel at all. And we can see if we are looking only at batteries, that the change from 90% CO2 reduction to 100%, it's huge. So you increase, you triple almost the cost from reducing from 90% CO2 reduction to 100%. But if you introduce hydrogen as an option, that it's working for a longer term storage, and you have a combination of battery and hydrogen, you get a higher price because it's more expensive just having renewables than the diesel case. But you don't get the costs are not as high as just using battery. So here it proves that using a combination of batteries and hydrogen is more profitable than just using a battery. And of course, this system is all given our assumption, and I think I showed, but if not, I can show you easily. We assume zero implication of CO2 tax. That means we could play around and change the CO2 tax to add this at an extra cost per emitted ton of CO2, and that would affect all the cases. So maybe we can find, one way is to find the optimal CO2 tax to kind of make all this 100% options more profitable than the base case. But that's that was just to give you an idea of what changes you can do, what other analysis you can do. So I think that was a good overview. I think that's also, this one is also interesting to look at, because that's how the load is covered. I can show you back how the system look like. So you can see this one. So we can this last kind of plot will show you how much of the load is covered either by the wind turbines directly, the solar directly, the diesel generator directly, or through the storage, either from the battery or from the hydrogen, depending on the case, of course. But I will show you the case where all these elements are present, so you can get a graphical view, because this is only for when you have diesel generator. But so of course all the load, which is this profile, will be covered by the diesel. But if we go to a case where we have this one, for example, it has wind PV doesn't install, so it's just wind batteries and hydrogen storage and diesel generator, because we are only covering 90% of the emissions. We can really easily look at how is this load covered for every hour. So sometimes we see just here is just the wind turbines, but you have some peaks, some parts that they are covered by your battery in this case. You can deactivate the different components, but it's really nice with this graph. You can eliminate some of the components to see what the others cover. So if we remove, what happens if we remove the wind? We see that the rest is what the other components cover. So we have the diesel generator, the fuel cell, and the batteries. So that way you can get an overview of how the different elements are covering your load for each hour of the operational period. And of course, they will depend a lot, the operation given, depending how realistically you model the operation. As we see here, there are some ups and downs, and that's because this simplified model doesn't penalize, for example, charging and discharging your battery all the time. So it will more likely to see these changes, like this hour is only the battery, next hour is only the fuel cell. But the more complex you model your case, then if you include the degradation or you penalize changing the operational or the production of your fuel cell, then that will make the profiles look a little bit more realistic. And that's what I mentioned before about the trade-off of modeling it simple enough that it runs, but at the same time the result has to be representative, because of course you can get a more realistic operation if you have a simulation model that doesn't take into consideration the investment. But the important thing of this model is that you include both the investment decision, the sizing, and the operation, although in a simplified way. And I think that's what I had thought to show you, because I had some results which are the same that I showed before, just in case the live of running things live would fail. But I think I showed most parts. I think I will finish here. So yeah, thank you a lot for your attention, and please let me know if you have questions or comments.
Thank you, Miguel, for your presentation. Very interesting. If someone has a question or comments, you can write them in the chat, or you can also activate your microphone, I think, and make the question.
I hope also I wasn't understandable enough. I know it's a lot of information to handle.
There is a question. There is.
Yeah, I have one question. Can you hear me?
Yep.
Yeah, it's a very nice presentation, Miguel. I was just wondering, you mentioned in your presentation that you had some, there might be like uncertainty, right, in these forecasts and these profiles that you're like using for your analysis and your assessments. I was just wondering if you try to do some stochastic, like optimization or try other methods to deal with that, or what are your views on this?
Yeah, we have in some project. In this case, simple case, it's just you have one year operation with so it's fully deterministic. So you know the expected load and the expected pre-production and the expected wind production. But in some other project, we have been trying to implement both operation uncertainties easier because we can have different parallel profiles and add them together to make a more robust investment. So you have a decision like investing capacity that covers all the possible profiles. What we have tried to do also was strategic decision, and thus seems to be much more tricky to get a value in limits. Take an example. That was in the Low Emission Center. It's another project where we have the carbonization of the oil platforms in Norway. So we had wind and hydrogen storage, similar as here. And here we try to compare what is the effect of different CO2 taxes and what was the effect of different capex evolution in the future of fuel cell and electrolyzers. And we saw it was quite tricky to get a different solution than the purely deterministic. So that's something we are trying to work on, try to find problems where they creating all these strategic scenarios, like different evolutions in price, for example, or in CO2 prices will affect the results. So that's one of the, but it has some, yeah, we're trying to, it's implemented, but we still need to find more projects to test it.
Okay, there are two questions in the chat.
Yeah. Yeah. Yeah, I think the first one, for comparing scenarios, you should set for each scenario a different parameter in terms of price. Or you can provide a forecast on how electricity prices or carbon tax could vary. Yes, you can add that into the JSON file. Here you can define the different strategic periods. So you can have different points in time where you invest. You can also add here in operational scenarios, you can define the different operational scenarios. So you can add them here as a list, and then you can add the weight. So you have different scenarios, operational scenarios with 25%, 50%, and so on probabilities to happen. And then the economic results will be multiplied by the weight. So it will be like in the objective function will be a sum of the costs multiplied by the weight. And then the system has to be sized in order to operate for all these profiles, let's say. So it will be more robust. And I think I can show you there's one of the cases if you go to the open model, open HyOpt, you have here the remote case. Here you have other two cases. The test case one is quite similar to the remote one, but the test case two, this one handles long-term storage, including stochastic modeling. So you can check the details here to see how it is actually implemented. And there is another question. Are there some use cases available for further studies, such as the master thesis or seminar based on your developed solver? There are, I think, only like completely open and only these three. So these are a basis. There are some publications, some reports on different projects, but I don't know if they contain enough information to reproduce it fully. You have the input, most of the input data. But for example, I can mention there are some analysis in the remote project, but although they are a little bit old because it was in 2019 or 20. In Helios, it's another European project. We have results. published, I think in Refine. It's on the European project where we have maybe some reports, public reports. The discount rate, it's that's, I think it depends. I'm not an expert in the financial terms, how the discount rate. It depends on usually if it's a public entity or a private entity, and are usually estimations. I think we typically work like 4 or 5%, but of course it depends on the case or on the client. If you are doing a performance analysis like this for a client, maybe they have their own expectations for discount rate. And I think it depends on the loans you get, but I'm not that expert in that bit. I can also send you my email afterwards, so you can also, if you have any other questions afterwards, you can always contact me.
Yeah, Miguel, the presentation will be made available. We
Yeah.
have registered the webinar, so it will be published online. It will be on the remote website. You can check it.
Perfect.
And we can also upload the presentation with your contacts so people can stay in touch and contact you in case they need.
Perfect. Then I will, I think my email is not added, but I will add it and send it to you, Marta.
Okay,
right now.
perfect.
The presentation, perfect.
Okay, I don't see other question. I don't know if someone has some other. In case not, we can also, I don't know, close the webinar, and as said, everything will be published and your contact will be added, so people can contact you.
Perfect.
Thank you.
And
thank you very much.
Thank you very much.
Everybody.